This article focuses on the green synthesis of blue titania nanoparticles through pulsed laser ablation in water, a method presented as environmentally friendly compared to traditional method.
The ablation process was carried out using a well laser L2000 machine. An experimental plan of 12 samples was designed by varying two waveforms, WP0 and WP10. For each sample, deionized water was placed in a beaker with the titanium target was submerged and the suspension was stirred. The laser moved in parallel lines 0.2 millimeters apart, turning on during each line and off between lines.
After laser ablation, the nano powder was weighed to check how much material was used. SRD and RAHMAN were used to determine their crystal structure, while TEM is used to examine their size and shape. In order to quantify their band gap energy, UV spectroscopy is used to evaluate the amount of light they absorb, and DLS is used to quantify their size in water to check the stability of the suspension. To sum up, this experiment characterized the nanoparticles' dimension, form compositions, and surface characteristics.
We evaluated the photocatalytic degradations of RR141 dye using both UV and visible light. The sample was prepared for 15 ml dispersion containing 400 ppm nanoparticles and 10 ppm of dye. Then the sample was kept in dark for 15 minutes under 500 rpm agitation to ensure any possible adsorption to occur. After this phase, sample was exposed to UV and visible light to measure absorbance at 544 nanometer using UVV spectrometer. Control tests with the nanoparticles were also conducted to check for photolysis and followed by the nanoparticles in the dye solution. Lastly, the result was compared with commercial TiO2 WO3.
For result and discussion, the bluish color of the suspension indicates surface defect in the nanoparticle. Over time, the particle agglomerated and fully sedimented but were easily redispersed using an ultrasonic bath. Zeta potential measurement shows value below negative 35 mV at pH 7, confirming a good colloidal stability. This was achieved through electrostatic repulsion without any needs for chemical stabilizer, as the particle carried a negative surface charge.
When we compare WP0 and WP10, WP0 had more energy, which gave a much higher ablation rate, about 60% more. Next, the faster the scan speed, the higher the ablation time rate. We also saw that with higher scan speed and lower ablation time rate, the surface looked much clearer under SEM. For the particle, TEM showed two shapes, tiny one between 8 to 30 nanometers and some speed light. Lastly, increasing ablation time made the particle bigger and more spherical.
For the photocatalytic dye degradation result, blue titania nanoparticles were tested for degrading reactive rate 141 dye under UV and visible light. Under UV light, they perform similarly to commercial titanium dioxide and tungsten trioxide, confirming their photocatalytic activity. However, under visible light, only the commercial catalyst show activity. Other than that, UV-based analysis show a 3.25 EV band gap for blue titania, which is slightly higher than titanium dioxide, which explains the limiting visible light absorption. It is hypothesized that although the blue color proved the surface defect, it was slightly insufficient to boost visible light photocatalytic performance.
In conclusion, the study had successfully completed its objectives, and the product has been successfully synthesized and characterized. Further research is recommended to adjust the setup for more homogeneous titania nanoparticles. Thank you.